G'day! Here's a classic textbook problem. It often appears on a unit on quadratics, and often appears on a unit on calculus as well, and it's this one. A piece of wire 1 unit long, okay, we've got a piece of wire 1 unit long, is cut to make 2 pieces. All right, so we cut the wire somewhere and make 2 pieces, a left piece and a right piece. We then take that left piece and bend it to make a circle. Okay, fabulous, a gorgeous circle. And we take the right piece and bend it to make a square. All right, great. We've now got a circle and a square made from that piece of wire 1 unit long. And the question is, where along this wire should you make that cut so as to optimize the sum of the areas of the shapes? The sum of these 2 areas. We want to optimize the sum of those areas. Now, optimize, what do I mean by that? Make big? Like maximize? Do we want to make it as small as possible? Minimize? All right, so we want to do something extreme with those 2 areas. So let me give those areas a name. Let's call this area 1 and area 2. So our question is to optimize, whatever that means, maybe maximize, minimize, the sum of those 2 areas. That's our task at hand. All right, so let me answer this question the way textbook authors probably expect me to do. First of all, let me get some variables in this equation. In fact, the natural variable to play with is the distance along the wire. I'm going to make that cut. 0 to 1, suppose I move x units along to make the left piece of wire. I've got a whole length of 1, so the right piece of the wire will then have to be 1 minus x. That seems the natural variable introduced here. So then the question is, I want to optimize a1 plus a2. Can I write a1 in terms of x? Can I write a2 in terms of x, those 2 areas? Well, let's find out. All right, so let's focus on the a1 first, the area of the circle. The only thing I know right now is I use that length x to make the circumference of the circle. The circumference of the circle is x. But I want the area of that circle, and the area is pi r squared for a circle. I need to know its radius. Do I know its radius? Actually, I do. Circumference is 2 pi r, so 2 pi r is x, so r must be x over 2 pi. Got the radius. In which case, area 1 is pi r squared, pi x squared over 4 pi squared. Some pi's cancel. This is 1 over 4 pi x squared. Area 1 is 1 over 4 pi x squared. Great, we've got a formula for it in terms of our variable x. All right, let's do the same thing with the square. I used a length 1 minus x to make the perimeter of that square, in which case one side length must be a quarter of that, 1/4 of 1 minus x. And area of a square is side length squared, so area is going to be 1 minus x squared over 1 over 4 squared, 1/16. There we go. So area 2 is 1/16 of 1 minus x squared. Great, 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 we're there. So our challenge is, our question is to optimize the sum of the areas. I'll just write big A for the 2 areas, A1, which is 1 over 4 pi x squared, plus A2, 1 over 16, 1 minus x squared. And let's be really clear, we're assuming here x is between 0 and 1. So we're doing this for 0 less than x less than 1. That is our challenge right there. All right, so as I give myself a bit more space, I'm noticing right away that we're really dealing here with a quadratic equation. I'm seeing x squareds and stuff with x's and numbers. Yes, this is a quadratic equation. I now know why it's in a quadratic units chapter. All right, so what else do I notice? If I look at the coefficient of x squared, I've got a 1 over 4 pi x squared, but when I expand this out, I'll get a 1/16 x squared. So I see the coefficient of x squared is 1 over 4 pi plus 1/16. That's a positive number. I know if I graph this thing, it'll be an upward facing U-shaped curve. Great. In fact, why did I graph this? That'd be kind of cool. Let me graph this thing and see what's going on. So here's the x-axis. We're going for x between 0 and 1. In fact, let's look at this extreme. X equals 0. When x equals 0, that vanishes and I'll get 1/16. 1/16. But what does that mean physically? If x is 0, it means don't use any wire to make a circle, use all the wire to make a square. So this is coming from using all the wire to make a square. The whole perimeter is 1. And if the perimeter is 1, that'd be a quarter and a quarter. Yep. And the area of a square that's quarter by quarter is 1/16. Yes. So that corresponds to the area of a square if I use all the wire to make the square. The other extreme is x equals 1. If x is 1, that vanishes and I'll have 1 over 4 pi. 1/16 compared to 1 over 4 pi. That's basically 1/12-ish. 1/12 is bigger, so I bet 1 over 4 pi is a larger number. But what's going on physically here? X is 1. That is, I'm using all the wire to make a circle. Don't bother making the square, in which case this corresponds to a circle of circumference 1. So there are my 2 extreme endpoints, what's going on there. And actually, it's an upward facing parabola, so the graph must be like this. Aha, aha. Beautiful. Oh, by the way, I did not have my parabola dipping below the x-axis. I can know physically I won't have negative areas, sum of areas. So I won't be going below the x-axis physically. And mathematically, I can see I'm always doing a positive quantity plus a positive quantity. I'll never be getting a negative value, at least in the range from 0 to 1. All right, or maybe ever. Okay, so that's great. So if you want to maximize the sum of the areas, I know right away, go here. Use all the wire to make a circle, and you'll get the biggest possible sum of areas. Great. And the minimum is going to occur here. So the question's really asking us to find what x value it matches that minimum value there, that minimum point there, the vertex of the parabola. All right, so if this is a quadratics class, I bet you have the formula x equals negative b over 2a for the coordinates of the vertex, the x coordinate of the vertex. I don't memorize stuff. That's not normally in my head. Or maybe better, if you want to actually take the derivative of this and set the derivative equal to 0 to find the critical point, check me, do that work, do either way, you will get that x is pi over pi plus 4. Double check me. All right, so that's the length of this part of the wire. Now the rest of the wire that gets me up to 1 minus x that gets me up to 1 will have to be, and I can see right now, it has to be 4 over pi plus 4. So if I add that and that, it gives me 1. Great, so that tells me where to chop the wire. Chop the left piece at pi over pi plus 4, and the right piece at 4 over pi plus 4. That is, I'll be a little bit strange here. Chop the wire at a pi to 4 ratio. I mean, it's really pi over that denominator, 4 over that denominator. Yeah, in a pi to 4 ratio with the total length being 1. There's the answer to that question. And if you want to actually know the minimum value of this, then I will just put in x equals this value into that formula and double check me, you get this beastly answer. It's horrible. The minimum area turns out to be, area is here, pi over 4, pi plus 4 squared, plus 1 over pi plus 4 squared. Whoa. So there we have it. I've got all the answers on my board right now. That's where the cut should occur. That's what the minimum area turns out to be. That turns out to be the maximal area. And that's all well and good. I've got full marks, but I don't feel satisfied. This is just grimy. I've got no intuitive feel for what's actually going on here. I suspect there's something deep behind all this. Let's explore. Okay, let's do the wire cutting problem again, but instead of doing a circle and a square, let's go crazy. For the left piece of wire, please make this shape. Whoa. Actually, what I really mean is, please make a scaled copy of that shape such that its perimeter is all x units of wire. All right, and for the right-hand piece, let's say we're going to make this shape. Actually, what I really mean is, please make a scaled copy of that shape such I'm using this amount of wire for its perimeter. There it is. This is wild. Okay, so let's see if we can analyze the situation for this particular scenario. Just to anchor my mathematics, let me do this. If I used all the wire to make that shape, so I used a scaled version of that shape, so its perimeter is 1, let me give that full area name. I'll call it alpha, say. And if I used all the wire to make that shape instead, so I get a bigger version of that shape, making sure I'm using all the wire for that, let me just call that area beta. So I'll use these areas alpha and beta as my reference marks for the maths I'm about to do. All right, so back here, I want this area and that area, and we want to optimize the sum of those two areas. Now to try to figure out how to get a formula for these areas in terms of our variable x. And the way I'm going to do that is go back to my reference points and say, well, really, if this is perimeter 1, I could just scale this back down to here to have perimeter x. Now, perimeter varies linearly with scale factor. So going from a perimeter of 1 to a perimeter of x means I'm scaling by a factor of x. Here's the thing. Area changes by scale factor squared. So area 1 must be the same as area alpha, but changed by the scale factor x squared. Area 1 is alpha x squared. We've got a formula for it. Same idea. This area 2, I'm going to scale this figure here down so its perimeter is 1 minus x. Scale factor is 1 minus x, which means area was beta is going to scale by that scale factor squared, 1 minus x squared. There's a formula for area 2. So our job is to actually optimize the total area. Area is a1 alpha x squared plus a2 beta 1 minus x squared. And again, we're doing this for x between 0 and 1. There is the problem in this general setting. Okay, I can still see it's a quadratic graph, a quadratic formula. which I can graph. It'll be an upward facing parabola, so let me graph it again. It was fun last time. I bet it's going to be fun this time too. All right, x is between 0 and 1. I put in x equals 0, that is, use no y for the left piece, use all the y for the right piece. I will get x equals 0, beta. For x equals 0, it's beta, value beta, which is using all the y for this piece. That corresponds to using this shape here of perimeter 1 and area beta. Great. For x equals 1, that means use all the y on the left piece. Put in 1, I'll get alpha 1 squared and 0. I get the value alpha. Great. Which corresponds to using all the y on this piece, perimeter 1, which indeed has area alpha. So whichever of these is the biggest value will be the maximal value of that quadratic function on that range. All right, so we've maximized it. For the minimum, well, I know it's going to be an upward facing parabola, like that. And there's going to be some minimal value at some input here. All right, so I just need to figure out the vertex of that parabola. Do you know what? I'm going to do it the school book way. So a little bit of space here. Let me just expand the brackets here. So this is going to be alpha x squared and a beta x squared, alpha plus beta x squared. I'll get a minus 2x and a beta minus 2 beta x plus beta. There it is. So when I want to find the coordinates, the x coordinate of that vertex, I would say x is negative b over 2a, and in which case that would be negative b is 2 beta over twice a, alpha plus beta, beta over alpha plus beta. The minimum occurs at alpha over alpha, beta over alpha plus beta. Smudgy, excuse me. Okay, let's get this right. Beta over alpha plus beta, great. So this length is beta over alpha plus beta, and the remainder of the length, what I need to add to this to get to 1, I see I need to add an alpha over alpha plus beta. There is the right-hand length, alpha over alpha plus beta. That is, I need to chop this length of wire to get the minimal sum of areas in the proportions beta to something and alpha to something, a beta to alpha ratio. This corresponds to x equals 0 using all the y on the right-hand piece, and this corresponds to x equals 1 using all the y on the left-hand piece. All right, so actually what I did last time was chop my wire in the ratio beta to alpha corresponding to these basic extreme shapes here. Okay, that feels interesting, but I still don't think I've really got it yet. What is really going on here? Here's a circle of area A and perimeter P. So I guess most people call that a circumference now. I might use the letter C. All right, so I've got a circle with those two quantities that I know about, area and perimeter. And I also know from my school days those two natural formulas that would go with those quantities. For example, the perimeter is 2 pi r and the area is pi r squared. But I'm going to be a little bit strange here. I'm going to pretend, well, hang on, there's no pi and r mentioned in my original setup. So to me, these are kind of like new symbols. There's pi symbol and there's r symbol. What are they? All right, so then you say, well, I can figure out what they are because I essentially have two unknowns I'm trying to work with and two equations in those two unknowns. I can actually solve for pi and r. So I'm going to do that. I'm going to be a little bit sneaky and start by working with this equation, but I'm going to double a, because I can see that double a is 2 pi r squared. That's 2 pi r times r. 2 pi r, that's p. Double a is pr, and there is a formula for r. Whatever that quantity is, I know it's twice the area of the circle divided by its perimeter, divided by its circumference. And now to solve for pi, let me use the first equation. So pi would be p over 2r's. I just worked out what r's are, so that's p over 4a's over p. Multiply top and bottom by p, I get p squared over 4a. Whatever this mysterious pi is, I know it's the perimeter of the circle squared divided by 4 times its area. Great! I can solve for r and p. So r is twice a over p, and pi is p squared over 4a. That is grand and good. There we are. So with these two values, I know these two equations are true, and vice versa. All right, but here's the thing. There's nothing special about circles, what I just did. For any shape, any old shape, here's this crazy shape of some area A and some perimeter P. I could define, associated to this shape, a natural pi value. Pi is going to be this perimeter squared divided by 4a, and its r value is going to be twice a over p, its perimeter. I'm going to declare that. I could do that for any old shape. I can just do it. I don't know what these quantities mean, but I can do that. And I know that these quantities satisfy the relationship that perimeter is 2 pi r, whatever pi is, whatever r is, and area is pi r squared, whatever pi is, whatever r is. I know those two formulas are true if I define those values for a polygon. Here's the nice thing. This is actually a constant. If I scale this polygon up by factor k, so I scale this up by factor k, then I know perimeter scales by factor k, so it'll become kp. Area scales by scale factor squared. This will be k squared a. So my new pi value for the scaled version of this polygon would be, my new pi would be kp all squared all over 4 k squared a. If I work that out, k squared p squared over 4 k squared a squared, I'm back to being p squared over 4a. So this value of pi is the same for the whole class of shapes similar to that one. Whoa, this pi is a constant for the class of shapes of that form, scaled versions of that. Great. Great, great, great. I have no idea what r means for that shape, but I've got a natural constant associated with all shapes now. This is really interesting. In fact, let me just quickly do an example with a square. Let's work out the pi of a square. So here's a square. I'll do an orange. I'll call it side length s. I know its perimeter is going to be 4 s's and its area is going to be what? It's going to be s squared. There we go. So I know that pi for a square is actually going to be, where is it? P squared, the perimeter squared, 4s all squared over 4 times the area, 4s squareds. 4 times 4 times s squared over 4 times s squared is 4. The value of pi for a square is 4. Which is really interesting, because when I did the first wire cutting problem, when I made a circle and a square, we said cut the wire in the ratio pi for a circle and 4 pi for a square. Oh, the ratio of pi values. This is getting intriguing now. Okay, let's do the wire cutting problem yet again, but this time let me associate everything with the pi values of the shape. This shape has a pi value. This shape has a natural pi value. I will phrase it in terms of those pi values. Alright, so with the first shape, I'm told its perimeter is x, but I know with these pi values and r values, its perimeter is given by this formula. So I'm really saying here that twice its pi value, I'll call that pi 1 for the first shape, times its radius value, I'll call that r1 for that first shape, is x, which tells me the radius associated with the shape is x over twice pi 1. Great, because then I can work out the area of the shape. Area 1 would be its pi 1 value times that radius squared, x squared over 4 pi 1 squared. Pi's cancel. I see this is really just 1 over 4 pi 1 x squared. Area 1 is given by that formula. All right, I'm going to be doing the same work here. I have a feeling it's going to be exactly the same. Twice pi 2 r2 is 1 minus x. So I'll be using subscripts 2 everywhere. Instead of x, I'll be basing on 1 minus x. And if you do the same work, check me. I'm sure it's going to be the same formula with all the subscripts now 2. And instead of an x, I'm really working with 1 minus x, and that gets squared. There's a formula for area 2. Alright, so our job now is to optimize the sum of those two areas. So I need more space, so let me erase this. Okay, I'm going to memorize these two formulas. Pi 1, yes, yes. Okay, got that in my head. Here goes. Here comes more space for us to do our work. So our job is to optimize the sum of those two areas for x between 0 and 1. So optimize the sum of the areas being, first one was 1 over 4 pi 1 x squared plus 1 over 4 pi 2 1 minus x squared. 1 minus x to make it a little bit neater. 1 minus x squared. All right. And this is for x between 0 and 1. 0 is less than x less than 1. Okay, all right. I can see this is a quadratic again. I can see all the terms are positive. I see it's going to be an upward-facing quadratic above the x-axis, and I'm doing it between 0 and 1. I can draw its graph. Okay, I've been here before many times today. 0 and 1. At x equals 0, I'm going to get just 1 over 4 pi 2. 1 over 4 pi 2. That corresponds to using all the wire for the right-hand shape. And if x is 1, if I use all the wire for the left-hand shape, I would get 1 over 4 pi 1. 1 over 4 pi 1. Great! Whichever one of these is biggest, I know that's going to be the maximal value of the sum of areas. Alright, so the maximal values occurs at one of the endpoints. The minimal value is going to occur wherever that vertex is of that parabola. So I need to find where that vertex is. We can do that. And this feels very familiar because I remember in the last section we basically did this formula. I had an alpha there and I had a beta there. It's just my alpha looks more complicated now and my beta looks more complicated now. But I do remember, so check me on this, when I do x equals negative b over 2a on this formula, I only get beta over alpha plus beta. I get 1 over 4 pi 2 over alpha plus beta, 1 over 4 pi 1 plus 1 over 4 pi 2. All right, that's where the minimum is. Double check me on that, but that looks beastly right now. So let me multiply the top and bottom by 4 pi 2 and by 4 pi 2 and also by 4 pi 1, 4 pi 1. Because if I do that, I can see x equals 4 pi 1 on the top over 4 pi 1 plus 4 pi 2. Cancel out the 4s. I'm getting very messy here with my board technique and not very good. Plus I'm getting very excited. X will be pi 1 over pi 1 plus pi 2. Whoa, there it is in terms of the pi values of our shapes. And 1 minus x, the rest of the wire, that which I need to add to that to get to 1 would be pi 2 over pi 1 plus pi 2. I'm loving this because this shows me, oh, I've got a fraction with the numerator pi 1 some denominator, fraction with the numerator pi 2 in the same denominator. I am basically chopping the wire in the proportion pi 1 to pi 2. Please chop the wire to minimize the sum of areas in the proportion of the respective pi values of the shapes. And when I did this for the very first example, we had pi for a circle there, pi, and pi for a square there, 4. There it is. It's really the ratio of the pi values. This is neat. Okay, I really think pi values are the right way to think about this problem. So let me quickly explain why I think that's so. So here's the situation we're in. Cutting a wire to make a left piece and a right piece of those two shapes with associated areas and pi values and r values and all the rest. And we found the sum of those areas at a minimum when we cut the left piece and the right piece at those values. All right, what I'm going to do now is actually work out those areas at that optimal situation. And I do remember area 1 was given by 1 over 4 pi 1 x squared in general. But at the minimum, x is going to be this value. So I can see in the optimal situation, area 1 is going to be 1 over 4 pi 1 squared over pi 1 plus pi 2 squared. I see a pi 1 cancels. This is pi 1 over 4 pi 1 plus pi 2 squared. So there's a formula for the area of the left piece in that optimal situation. The area of the right piece in that optimal situation would be the same formula, if I remember, as this, 1 over 4 pi 2, 1 minus x squared. Okay, except 1 minus x, the optimal situation is this. So it's going to be 1 over 4 pi 2 squared over pi 1 plus pi 2 all squared. Pi 2's cancel and leaves me with pi 2 over the same denominator, 4 pi 1 plus pi 2 all squared. Whoa, I can see it. All right, at the optimal situation, we have these two pieces. The wire is cut in a pi 1 to pi 2 ratio. That is, the circumference of this piece to that piece is a pi 1 to pi 2 ratio. But look, the areas are also in a pi 1 to pi 2 ratio. Everything is in a pi 1 to pi 2 ratio in this scenario. Whoa, I can see that with the pi's. In fact, let me summarize everything we've done by drawing a graph. Let me draw one ultimate graph to end off today. I need more space. Okay, the ultimate graph, here it comes. All right, so I'll draw my x-axis between 0 and 1. All right, at x equals 0, don't use any wire for the left-hand piece, use it all for the right-hand piece. So we'll be doing this. Make the right-hand piece using all the wire. Perimeter is 1. Now if you recall, I called the area of that piece beta. So the value of this function at 0 is beta. The other extreme, use all the wire for the left-hand piece. So I'll get a shape like this, using all the wire to be its perimeter. And if you recall, I called that area alpha. The other extreme is actually use all the wire on the outside piece, area alpha. In between, we do know there's going to be some minimum somewhere. So at this minimum, we're going to get two pieces, a version of this plus a version of that. So I'll have something here of area A1 plus something here of area A2, and we found where that cut has to be to get that minimal value of the sum of the two areas. In fact, we saw cut in a pi1 to pi2 ratio. We also saw today cut in a extreme beta to extreme alpha ratio. I should put these in inverted commas, these aren't the actual lengths, but cut the sections in those ratios. If you do that, more is true. Turns out this area to area 1 to area 2 is also the pi values ratio. Great! You also get the perimeters here. Perimeter 1 to perimeter 2 is also the ratio of the pi values. But it's really that statement up there. But there it is. Ratios of pi values left, right, and center all through this problem. Pi is the way to go. You've just got to love this notion of pi for a polygon. It's grand. Okay, so here's the graph, the ultimate graph of everything. So we've got the x-axis, which is in 0 to 1. All right, so here at x equals 0, we use no y for the left-hand piece, use it all for the right-hand piece. So I'm making a shape that's the right-hand piece with all its y going towards its perimeter. All right, good and grand. But if you recall, I gave a name to the area of that shape. I called it beta. So the value of my function at 0 is beta. The other endpoint, that is I use all the y for the left-hand piece, give me something over here, so let's make this shape, you make sure all the y is used for its perimeter, gives me that shape, whose area I called alpha. So this extreme has value beta, this extreme has value alpha. Grand and good. In between, I know it's going to be a parabola with some minimal value somewhere. Okay, there's the minimal value. And at that minimal value, I will get a left-hand piece, this shape, plus a right-hand piece, this shape. It'll have some area here, A1 has some area there, A2. Grand. Now, where do I cut this y? We cut the y in the ratio of the pi values, pi1 to pi2. Great, we got that. We also showed you cut the y at the ratio of the extreme endpoint values, beta to alpha. Turns out to be the same thing. And when you do that, you actually get two shapes here whose circumferences are, well, pi1 to pi2, that's not very exciting, but areas are given by the ratio pi1 to pi2 as well. Everything is pi1 to pi2. Even the two extreme examples are in a pi1 to pi2 ratio. This is why I think pi's are the way to go for this problem, and you guys love this notion of a pi for a polygon. It's just wild!